Thank you for being with us today. I'm happy to see all of you here for this talk, which is part of the CIS COLLOQUIUM. With these seminars, we provide a platform that brings together professors and researchers from EPFL and researchers and thought leaders from all around the world working on different aspects of intelligent systems. In June, prior to our short summer break, we had the pleasure of hosting Professor Vijay Kumar for a talk about swarms of small flying robots. Today, we're delighted to have Professor Allison Okamura with us. Allison is a professor in the mechanical engineering department at Stanford University with a courtesy appointment in computer science. Just briefly to give an idea of what to expect, the talk will last for approximately 1 hour. It's Professor Okamura presenting for 45 to 50 minutes. The talk will then be followed by a Q&A discussion that will be moderated by Professor Alexandra Lahi, who is the head of the Visual Intelligence for Transportation Laboratory at EPFL. So please, if you have any questions to your talk, feel free to submit them directly via the chat. I will take them up later on for discussion in the Q&A session. Before we dive into the presentation, I would like to thank Professor Okamura for her availability and the entire CIS team for organizing the event today. So please join me now in welcoming Professor Alahi for the words of welcome for our speaker.
Thank you, Jan. It's a great honor to introduce Allison. As you said, she did her undergrad at UC Berkeley, then PhD at Stanford. She's now a full professor at Stanford, affiliated to 2 departments, the mechanical and computer science department. She's also the deputy director of the Woods-Tsai Stanford Neurosciences Institute. She has been the editor-in-chief of many journals in robotics. She won many awards. Her most recent one is in 2020, I guess maybe before the pandemic, or the IEEE Engineering in Medicine and Biology Society Technical Achievement Award. She's extremely well known internationally for developing the principles and tools to realize advanced robotic and human machine systems capable of touch interaction. She applies it to a medical application such as teleoperated robot assisted surgery. And today she will talk about wearable haptic devices for ubiquitous communication. Thank you so much, Allison. We're looking forward.
Hey, thanks so much for having me. I really wish that I could be there in person. I've had the opportunity to visit EPFL a number of times and seen many of your labs, especially over the last 5 years. Hope to be back soon. But in any case, thank you for accommodating my California schedule. I know it's evening for you, so I hope you are relaxing and enjoying your dinner or something simultaneously to this talk. So let me share my screen. All right. Yeah, so I decided to talk today about wearable haptic devices. So to give, actually, before I dive in, I should put my thank yous up front so I don't run out of time at the end. So I want to thank all the students who contributed to this work. So a number of these students actually have recently graduated from my lab and luckily gainfully employed even during the pandemic at universities or companies. And they're really the ones behind the results that I get the privilege of presenting today. So the motivation for this work is to enable physical connections between people. And of course, this is something we've acutely felt during the pandemic as we require more and more remote communications. And it's been shown in many scenarios that lack of physical interaction can affect these communications, particularly in human-human relationships. So one thing that we're aiming for is haptic devices that enable us to have social emotional touch, which I'll especially focus on at the end of the talk, in these types of environments. But of course, there are lots of other scenarios where wearable haptic devices might be useful in our environment. For example, instead of staring at a map on the screen or trying to listen to multiple different types of sounds at once, we could use haptics as a sort of underused channel of communication that an agent might, for example, send us information about when to turn left and when to turn right. In addition, as robots become more ubiquitous in our homes and in our work environments, there may be ways that they can provide us with communications that don't directly distract from our other sensory experiences. So human-robot communications is another type of application where the sort of physical connection might be useful. Now, when we try to come up with a rationale for what is the sensory modality that we choose to communicate in these ways, People always wonder, you know, why not sound? Why not vision? And because vision is the primary modality we use for interacting with much of the technology around us, I think it's useful to compare vision and touch. And you can see their dual nature, and this will also highlight some of the challenges that we have in creating useful haptic devices. So one comparison is the location of the sensors. The eyes are, of course, relatively centralized, you know, in the front of our head, whereas touch is distributed all over our whole body. And yet our eyes can, through a relatively small area, sense a very broad spectrum of the environment. Whereas touch is pretty narrow in that if I'm making a physical contact, that only occurs very locally, although of course I have tactile sensors all over the skin. The way in which we need to interact in order to acquire the sensory data is also very different. Now, anyone that does research on vision knows that eyes are not truly passive. We have saccades. It's very important to be able to move the eyes around. But relative to the idea that to touch something, you need to expend energy to go over and interact with it. And if you have a haptic device that you need to be able to power it, usually at some expense, in order to create this active physical interaction, touch is, I would say, much more active of an interaction modality than vision. While of course all sensory modalities can be extremely cognitive, and vision is no exception, there are a lot of aspects of touch which are kind of inherently physical in nature. The dynamics of interacting with an environment affect what you feel, that's the physics, but in addition, we have low-level reflexes that will actually cause us to react, and that can actually occur even without a cognitive realization. So the environments in which we would like to actually exploit this sense of touch, there are many of them, and a lot of research gets applied towards some very specialized types of scenarios. So of course, a very famous one would be a person that's wearing a prosthesis. There's no more literal removal of the sense of touch and the need to feed it back through an alternative method than actually losing a limb where you would no longer be able to access the sense of touch on that limb. So one example would be, how do you provide haptic feedback in a wearable device as the one that's mounted on the chest of this amputee here that can provide haptic feedback, replacing the lost sensation on the limb. And then there are specialized professions, whether it's a demining, like in a military or a police scenario, teleoperating a robot on the space station or space shuttle, and teleoperating a robot-assisted surgical system where you have a remote robot representing basically your hands in the remote environment and you want to receive feedback from them. But these are all very specialized scenarios. So the last image in the lower right of the screen shows something that's becoming much more commonplace, and that's virtual reality and augmented reality, which is going to become more ubiquitous for learning and training. And some of the old-fashioned haptic devices that sit on your desktop and cost $30,000 and provide extremely compelling haptic experiences are not going to function as we want to move to mobile devices and training scenarios where regular people would like to use these for interacting with computers on a day-to-day basis. If you compare that to what we have now, so this is a famous illustration actually from many years ago from Tom Ego that represents this is how your computer sees you. You're basically one eye, because you hardly ever have stereo feedback to humans interacting with computer systems. You might have stereo sound, and usually you're interacting with just one finger, maybe a couple of fingers, but even that doesn't tell the whole story because you don't get normally very sophisticated haptic feedback from these systems. You might get vibrations, which typically displays an event cue, but you don't feel a kind of natural interaction. So the types of traditional haptic devices that I was just railing against that we want to go beyond looks like this one. And actually, I have nothing against this haptic device. I probably have about 5 of them in my lab at great expense. And they are basically desktop robots that you program to output forces at different locations in the workspace. You backdrive it with your hand, and they're designed to be very lightweight and backdrivable, such that you can make free space feel free and hard objects feel hard. And you can actually render a number of different compelling environments. The problem is, as I mentioned, the cost, the mobility of the devices are really going to prevent the future world of consumer applications where we have to haptics more integrated. And so we're interested in going beyond these force feedback haptic devices, which are really based on principles in robotics, and looking at tactile displays instead that deform the skin with much less force required and the ability for them to become mobile. So you might wonder, how important is this feedback just to the skin? It's called cutaneous sensing or feedback, compared to this force feedback that you would get from these more expensive devices. And I love this example from Roland Johansson's lab from the early 80s, where he showed an example of how important this cutaneous feedback is in our manipulation. So the video on the left, which is playing right now, shows a woman striking a match, and she does it very quickly and easily. And the video I'm going to show you on the right, she's had her fingertips anesthetized. So she's lost her local mechanoreception, her cutaneous sensing in her skin, but she can still feel forces through the muscles and tendons in her arm, which attach to the fingers. She has full vision, and you will see how awkwardly she performs the same task. Okay, so what she's missing now is knowledge of the local contact conditions between her fingers and the matches, which are really impeding her ability to manipulate. And she eventually gets it, but remember, this is with all of her other faculties in place, right? She can see, she can feel forces, she just can't feel on her skin. So it's not that different from how you would manipulate if you're wearing thick rubber gloves. And I will be mostly focusing today on haptic feedback to humans. And so I won't talk about robot haptics, but you can also see, as an example from this video, how hard it is to get robots to do these dexterous manipulation tasks if they don't have these embedded tactile sensors in their robot skin. So by showing you what happens when we take away cutaneous sensing, I hope to sort of emphasize its importance. But of course, what we're going to be doing in our work is keeping cutaneous feedback, but removing the kinesthetic or large-scale force feedback. And when we focus on cutaneous sensing, we do need to know a little bit about the neuromechanics of the skin. And this is a very simplified view, but I think it gives a nice overview that I guess highlights both the challenges and the opportunities you have with creating tactile or cutaneous haptic displays. So when we push on the skin and we recognize that there's been some sort of stimulus, this recognition is going to be due to neural firings and our own perception. And the neural firings are coming from these mechanoreceptors, these sensors embedded in the skin. And depending on the type of mechanoreceptor, it might respond to different frequencies. For example, the pituitary corpuscle is famous for allowing recognition of relatively high frequencies and providing a very strong salient response. And so if you want to get someone to pay attention to something quickly, you display a high frequency vibration and your pituitary corpuscles go nuts. You have these other various mechanoreceptors which respond to lower frequencies. And another important point is that their density, the spatial distribution, the field of reception they have all vary. And another important thing is that it depends on the type of the skin, which mechanoreceptors are present and how dense they are. And when we're thinking about wearable haptic devices, much of the early work in my lab and many other labs focused on putting wearable devices on the fingertips, which made sense because this is the glabrous or non-hairy skin. It has a very high density of mechanoreceptors. If you've ever seen one of these sensory homunculus pictures where it sort of scales different parts of the human body based on how much perception or movement it has, the hands are just gigantic compared to other parts of the body. because of this density in the skin, in this non-hairy skin. So the challenge, however, is that if we put haptic devices on the fingers, then we can't use the fingers for other things. And this is really important, for example, in augmented reality. So we would like to move haptic devices to other locations on the skin. For example, the arm. This is unused real estate. We can do stuff here that it won't get in the way, hopefully, if you've designed it well, of other things that you might want to do with your hands. However, this is hairy skin and it has a much lower density of mechanoreception. Other parts of the body, for example, your back, are even worse. And so as we consider where we're going to actually stimulate the human body, it's important to know the distribution of the mechanoreceptors and how do you match the device that you design to that location on the body. So let me walk you through some examples of different types of haptic devices and then get towards this important question of how do we move from the fingertips to other locations on the body. So one of the first things I want to mention is that in the real world, of course, we experience a combination of kinesthetic and tactile feedback. So we get force feedback as well as information fed back to the skin. And I would say the most type of literal haptic display that exists that can stimulate everything would be an active surface, which provides both kinesthetic and tactile. And many different researchers have come up with approaches for this. And I thought I'd throw out this one from my lab because it's a lot of fun. It's a soft haptic device. It's really a soft active surface which changes its shape and mechanical properties based on a combination of positive pressure from below, which helps it change shape, and then vacuuming the air out of a set of 4 cells, where each cell is filled with a granular material, in this case, coffee grounds. And when you vacuum air out of an area with coffee grounds, the coffee grounds lock together and they become stiff. And so you can see this weird surface changes its shape and mechanical properties through a sequence of activation. And we have algorithms to plan if you want a particular shape and mechanical properties, that this is the sequence of actuation that you need. So this is a lot of fun, but it's also a lot of work, right? Trying to create a haptic device that just physically recreates the world. It doesn't take advantage of haptic illusions and tricks and elegant things that you might do to make haptic devices, actually be feasible in terms of cost and use in daily life. So while a lot of fun in terms of making a soft haptic device, this is not going to be the way to go for these ubiquitous wearable haptic devices. So what is possible? Well, let's go back then to the opposite end of the spectrum, to the very simplest thing you could build. And I mentioned that the Pacinian corpuscles as a mechanoreceptor are great in terms of responding to high frequency vibrations. And it's also very easy to put vibrations into our devices. You know, all of our mobile phones will vibrate in order to alert us if there is a call coming in. But like I said, typical vibrations are really limited in the type of information they can convey. It just kind of says, hey, I'm here, I'm vibrating, pay attention to me. It doesn't usually have the ability to communicate information. So we've looked at how can we take vibrations and make them a little bit more sophisticated in ways where we can communicate more than just an alert. So one example of doing this, and other groups have done this as well in some different formats, has been to create asymmetric vibrations. So instead of just displaying a sinusoid, you display a waveform like the one on the lower left here, which kind of creates a large push in one direction and then a recovery. And overall, there is a net sensation that there's a tugging in a particular direction. And there's another interesting aspect of this, which we don't fully understand, and our neuroscience collaborators don't fully understand, so we're still studying it, which is that not only do you feel a tug in a particular direction, but if it's done just right, and some people react to this more strongly than others, you feel compelled to move in that direction, which is a little different from just feeling a tug and then noticing it and responding to it. You actually really want to move your hand. We found this is really compelling when we have vibrations going the opposite directions on the thumb and the forefinger, and people want to really turn their hand all the way around, and they'll even spin around in the lab during the demo because it really makes them want to turn. So we're not quite sure yet how to operationalize this or why this effect seems to be stronger in some people than others. But it can be a very strong sensation and could be used to guide people's movements, for example, in virtual environments, or provide them with directional information. So this is sort of getting to the point of, okay, what can we do that's like cheaper, that's practical, can be used with off-the-shelf actuators that you might actually start to be able to put into mobile devices. But let's say we want to go, actually, before I go on to more sophisticated devices, I want to mention one other cool thing that we can do with vibrations. And this is kind of different from the other purposes of this talk, but it's still pretty compelling, so I wanted to describe it. And that is using these vibrations in order to help recover from movement and sensory deficits after stroke. So many patients after stroke have spasticity and poor muscle tone. They're not able to perceive also through their skin. And the nice thing about vibrations is they can easily be put into a passive tactile stimulation device that's wearable. Doesn't necessarily have to be on the fingers or on the fingertips. So we've created devices that have distributed vibration along the knuckles, and have been able to demonstrate that after just receiving these passive vibrations and not having to make any movements at all, compared to a control group, patients that suffered from movement deficits after a stroke had improvements, that is, an increase in their ability to move and not be restricted by spasticity after having worn these devices. So there are still not fully resolved scientific hypotheses about why this works. Regulation of electrophysiology associated with spasticity is one, and another is that sensory stimulation increases excitability of motor systems. So we feel like, well, these questions are not fully answered. We do have work now that's indicating that stimulating the skin is all that is necessary for improving sensory understanding, as opposed to stimulating, say, the muscles and the tendons directly. So this is a very simple wearable take-home device that can be ubiquitous for stroke patients, and they don't have to go into a clinic to use it, and they don't even have to be able to move, as is required in many rehabilitation scenarios developed in the field of robotics. But now let's go on to some, I guess, more sophisticated types of haptic devices. So this is a device that was developed in my lab, I guess about 5 years ago now, which really changed our thinking about what you could display through tactile stimulation alone. So what this device does is it pushes a little red tactor onto the skin, and it has 3 degrees of freedom with a little robot delta mechanism. It's basically like wearing a little delta robot on your fingertip. And it pushes in XYZ to provide normal force and shear force on the fingertips. And then when you interact with virtual objects, like is shown on the right, if you pick something up, then what we do is we reproduce the skin deformation, or something similar to the skin deformation that would occur if you were really picking up a real block. Now, this is different from kinesthetic feedback, because if you actually had a real hand exoskeleton or a world-grounded haptic device that provided force feedback, if you grasped an object, you would not be able to push your fingers together. These devices are only stimulating the skin, so nothing is preventing your fingers from coming in and making contact with each other. But what we found is that for manipulating lightweight objects, and this is true in the real world as well, the forces that you interact with are small enough such that you don't really need that kinesthetic feedback. We get most of our information from the cutaneous or skin feedback anyways. And so these devices, even though they don't have force feedback, they only have skin deformation feedback, still provide a lot of the useful cues that you need in order to manipulate these virtual objects. So it's pretty compelling, and you can see that the subjects in the experiments that we did sort of manipulate very naturally, even though they're only getting cutaneous feedback. So of course, we tested this. I'm avoiding showing you lots of plots and psychophysical results in this talk, but let me give a kind of high-level example of one thing that was really important for us to do. So in the field of haptics, it's very common to do these kinds of A/B experiments, where they say, oh, okay, we've changed the mass of this virtual object. Here's mass A, here's mass B. Are they different or are they the same? And then you identify a just noticeable difference, so you can see how well does this haptic device help someone in differentiating this mechanical property. And we do this all the time, but the problem with this approach is that often people are really just responding in terms of how they feel about the intensity, and it doesn't get to the realism of the virtual environments that we're trying to display. So what we did in this study with these haptic devices to really try to understand how realistic objects felt when we just provided this sort of skin deformation feedback is we showed pairs of blocks, a red block and a green block, and we didn't tell the subject how they were different. Sometimes we changed the virtual mass of the object, which means that the skin deformation feedback the user would receive would change dependent on how heavy the object was. And then some of them we changed stiffness, and some we changed the friction coefficient. And we, instead of sort of prescribing an A versus B type of experiment, we asked our subjects, just pick up these two blocks and tell me what you think is different about them. And sure enough, if we change the mass, people almost always said that they thought the mass had changed. If we change the friction without giving them any hints about as to what had changed, they would use words that would describe friction. Now, not all of our subjects were engineers, and so some of them kind of would come up with creative words like heft and stuff like that. And so we kind of did some text analysis to understand, okay, they're probably talking about mass here. Or friction or stiffness. So one of the interesting things was that with stiffness, people often identified a change in stiffness of the virtual object as a change in mass. And it turns out that with real foam blocks, people also can mix these up. But not as bad as they mixed it up here. So in this case, you can see a lot of people thought a change in stiffness was actually a change in mass. And the reason is that in order to apply more normal force, and sometimes friction, in order to apply more normal force, they had to squeeze the object harder, but you also need to squeeze the object harder if you have lower friction or higher mass. And the stiffness, it seems, people expect to feel larger forces when they push on hard objects, and they expected these blocks to be kind of solid. And so stiffness may not work as well without the kinesthetic feedback. Like the skin deformation feedback alone wasn't necessarily enough to give a realistic feeling of stiffness, but for other properties, it worked quite well. So this tells us something about the realism and the types of things that you can display that feel realistic with these types of devices. So one other thing that we can do that's not just about feeling virtual environments and realism is sending useful information to people. So we were interested in a project where a holdable haptic device would provide navigation cues. And this was kind of a subset of a larger project done by my graduate student, Yu-Hong Che, pictured here, which involved guidance with mobile robots and such. But we'll forget about the mobile robot now and just think about haptic devices trying to guide people to walk around. And this could be useful for anyone, but we're also interested in navigation aids for people with low vision. So what we found when we had people touch this haptic device and it tugged on their finger in different directions is that people didn't actually respond quite like we thought they would. If we tugged in the forward direction, yeah, they would walk forward. But if we tugged a little bit off from forward, people still like to walk forward. So we found that if you take a subject and you collect a bunch of raw data about what kind of haptic stimulation you give them and where they actually go, it's not a straight line, and you can actually come up with a model. You can learn the human responses to the haptic cues. And interestingly, this seems to be particular to haptics. So if we gave them auditory feedback and said, you know, go 30 degrees to the right, like they would do it. They would do it fine. And so people were taking this kind of implicit sensory cue and kind of mapping it differently. And they really like to go in the cardinal directions, forward and backward, and maybe directly turning left and right, but they didn't really like to go in between. And that explains the shape of this curve. We also found that different people had different curves. So we learned human responses to haptic cues, and then we took those learned responses in order to effectively teleoperate people, to drive people to targets. So if we didn't take into account our learning of a particular human's response, and we had them start at a starting location and try to hit these gray dots as targets, this is just maps of people walking around the space. We would have to kind of re-steer them and have some sort of feedback control to get them to the target. If we optimize the feedback based on our learned model of how a human responded to the cues, then they did much better. But we also wanted to try a method where we didn't give feedback all the time. We only gave feedback on an as needed basis to correct deviations in trajectory. And there they don't do nearly as bad as naive, but also not quite as good as optimized. But maybe that's good enough if we don't want to have to constantly be driving the motors to give somebody feedback. So this is interesting because it's showing that this type of skin deformation feedback is not just useful for realism, but it's also useful for human guidance. However, we need to take into account that people don't always respond as we expect to this kind of stimulus. And I'll also briefly note that we've tried this in higher degrees of freedom with a holdable device with pairs on the thumb and forefinger, and we can communicate many more degrees of freedom than just walking around in the plane. And one thought with this is it could be used, for example, for training people to make dexterous movements like that in surgery, but now in a much lower cost holdable haptic device compared to a world grounded, very expensive kinesthetic device. And before I move on to going away from the fingertips, I just wanted to give a brief plug for educational haptics. These devices actually are not all cutaneous devices, but if folks are interested in hand-based haptic devices, we have these publicly available designs for the HapKit. Actually, I don't have the URL in here, but it's hapkit.stanford.edu. And basically, you can build your own haptic device and be able to program it. We have like an online class, and lots of kids have used these as well. You can sort of act like they're haptic Legos and scale them up to higher degrees of freedom. And we've even used them in a different version of this in some math education to understand how do you improve math learning when you combine haptics and solving math problems. So that was just sort of an aside, because what I want to do now is move away from all of this stuff on the fingertips to dealing with other parts of the body. And just keep in mind that we really think that moving away from the fingertips is going to be important in order to have these more ubiquitous haptic devices and applications. So as I mentioned, we have much denser coverage on the fingers than we do in the arm and other places where we have hairy skin. But there's one other issue which I'd say we're still struggling with. We have not yet solved, and this definitely affects sort of realism and how people respond to these haptic devices. And that is the difference between active touch and passive touch. So when we interact with the world around us, we are very attuned to using active touch to learn about the mechanical properties of objects. So for example, on my phone here, this surface has a nice texture to it. Because of the frequency response of the mechanoreceptors embedded in my skin, I don't learn much about this surface, even on an edge like this, by just holding my fingertip there. I have to move my finger back and forth in order to do a kind of persistent excitation in order to receive lots of useful information at different frequencies that tells me about the world around me. And part of the design of our hands and fingers is to allow us to do that kind of haptic exploration to learn about the world around us. When you're providing haptic feedback at a different location on the body, you don't naturally kind of explore the world with this part of your body, right? I don't go and rub it on the back of my phone in order to learn about the texture. And so some of the things we're interested in are, okay, if you're going to provide haptic feedback in this location, could you kind of virtually explore with your fingers, but feel the feedback here? And so far, it looks like that does work pretty well, but not to the extent that it works with the fingertips. In addition, we found that it's useful to prime people. So if you're going to give somebody passive touch, you often want to send them an alert first that, hey, I'm about to send you a signal so that you can pay attention to that area. And then you send the signal that actually has to be received, because these signals are now just kind of coming into the user, not necessarily being initiated by the user. So it's like, if I want to send a haptic emoji that someone says, you know, have a good day, it's like a pat on the back. It is very temporal, right? You feel it and it goes away, as opposed to like looking at an emoji on your cell phone. And so if we want someone to feel it and catch that feedback, we may have to prime them to bring their attention to it first. So this active versus passive touch has a few different facets that you'll probably kind of see arise in the coming projects. All right, so first of all, as we move away from the fingertips, we want to know where in the body do we do this. So I'll kind of give away the punchline now, which is that most of the work that we've done has been on the forearms and on the wrists, because this is where people are actually very comfortable having devices applied to them. But it's been very interesting that we've also found that the neck and the upper area of the head is also a great location for providing haptic feedback. People can actually really notice stimulus here. And before I get into more practical applications, I thought I'd mention a really interesting study where we use this information that the back of the neck can be a great place for haptic feedback with a patient who actually had a spinal cord injury. So he has no sensation or movement from basically the upper shoulders down. And this patient is part of a multi-university brain gate study where they have implanted an electrode array. We record neural activity. A neural signal decoder is used to send a command that can be used to, for example, control a cursor on the screen in our case. And of course, it can be used to also control robot arms and other objects. And yeah, some of this work has been done at a number of different universities. In our case, we wanted to know if we could improve cursor control if we provided a command signal from a haptic device. And with this particular patient, there wasn't much, skin real estate to use because he lacked perception from the shoulders down. And so we applied feedback to the back of the neck. And we found that we could get responses in the motor cortex that could actually be measured with the electrode array. And it could be provided as feedback in invasive brain-computer interface control, and it didn't interfere with brain-computer interface performance. And so really briefly, the way this looks, so in this video, the patient is basically thinking about moving the cursor to different locations. An electrode array, which hopefully you can see my cursor, is here, which is implanted in his brain. And simultaneously, based on what we're measuring from his brain signals, we are controlling the haptic device to give feedback about where the location of the cursor is going. And we found that his perceptual accuracy about where the cursor is going is actually a very close match to the neural decoding accuracy, which is not perfect, by the way. That's still work that's ongoing. And we're on the path to try to give useful haptic feedback, because as we start to have these brain-controlled interfaces being used for, say, manipulating with robot hands and fingers, it's going to be important to know when you've made contact, when the object is slipping from your grasp. And at this point, we definitely don't have the sophistication to provide feedback directly to the brain. And so we're using these external haptic devices to achieve that. So just as the neck, as an example of a place we found that we can give useful haptic feedback. But of course, this is not going to be the most practical thing for consumer devices for most people. And so we're very interested in the wrist and the arm. So my recently finished postdoc, Mini Sarach, has developed a number of different devices that mount on the wrist. And she's shown that very similar to the examples that I showed earlier of the fingertip haptic devices, if she tracks the fingers as people manipulate virtual objects and then gives the feedback on the wrist, people can still identify virtual object properties like mass and stiffness and friction, similarly to how they did with the fingertips. It's not quite as good because our mechanoreceptors are not as good, but we're also not yet really taking advantage of all the space that we have here. We're just pushing on the skin and shearing the skin locally, just like we were at the fingertips. And we know the skin here just doesn't have the same density of mechanoreceptors, but fundamentally the task can still be done. So what we wanted to do next was think about how do we start using more of this skin real estate to do different things? And also how do we make these devices more comfortable and wearable? So I don't think that we're anywhere near a final answer or success here yet, but I thought I'd show you a couple of examples of different concepts for soft wearable haptic devices that can display different types of signals. So the one on the left uses a very traditional fiber reinforced elastomeric actuator, which is sort of in a cross configuration so that a single point of contact can push in the skin in multiple directions. And that is effective, similar to the sort of hard devices I showed earlier. In addition, we have on the right a kind of weird device that is built on this concept of a soft growing robot, where we have these soft everting tubes that can lengthen and change their shape. So we have this kind of bracelet that houses this soft plastic material, and then it can grow out of the housing and wrap around the wrist. And then we can pneumatically actuate it to have different contacts at many different locations over the skin and kind of take advantage of the unused real estate here. So in this case, each haptic actuator is a little pouch embedded on this plastic, and we touch the skin at many points, and then each one of those points is very simple. It just provides one direction. So these are some kind of contrasting approaches, and we definitely feel like the one on the right, which uses more contact points, more skin real estate, is going to be more effective given the mechanoreception on the skin here. The thing that we're working on is how do we put the bracelet back into, or how do we put the plastic back into the bracelet afterwards? These kind of retraction devices are a little bit bulky, but the idea would be, oh, when you're done using it, it goes back into the bracelet and puts itself away. I think I'm gonna skip this. So the last topic that I'd like to cover is social touch. So how do humans communicate information with each other, and can we reproduce that with some distributed haptic devices that we place on the body? Of course, social touch is key for communication, as I mentioned earlier. And this is an example of me stroking my husband's arm with a classic kind of I love you or calming type of signal. So it turns out that when people make these kinds of movements, there was recently discovered a new kind of mechanoreceptor called the CT afferent, which fires when you give these kinds of stroking behaviors. And so this is what we wanted to recreate with a haptic device. So this first version was developed by Heather Culbertson, and what she did is she figured out through a series of discrete normal pressures on the skin, if she got the pattern just right, you would feel both a pleasant calming sensation and a continuous sensation. So I briefly mentioned earlier this idea of haptic illusions. So rather than literally, say, taking a robot finger and stroking on the skin, can we give the illusion of a continuous stroke by having a device with different contact points and have them patterned in a particular manner that would feel pleasant and continuous? And this haptic illusion basically exploits the fact that our tactile sensing and our perception is not perfect, because we take shortcuts just like we do with visual illusions in order to interpret what we feel. So it turns out that there are a number of different ways to give this continuous stroke illusion. So this one is the example I just showed with these discrete little voice coil motors that they're not being used to vibrate. They're just pressing on the skin somewhat slowly. We were also interested in, should we create devices that actually provide a little bit of local sliding, and would that enhance the effect? And actually, it turns out it doesn't really enhance the effect. Having just voice coil motors that push into the skin gently is just as good as a distributed array that also provides some local sliding, which is a good thing because this lower array is way too big and clunky to ever be wearable. So it turns out it's good enough to have a simple distributed display, and actually you can move these contact points apart pretty far, a couple of centimeters, and people will still feel this effect of a continuous feedback. And I'm just gonna skip over the details of those illusions and kind of get to the penultimate experiment, which just got accepted yesterday to a journal. So I can tell you about some of the details of this. So the idea here is that we wanted to capture and recreate these social touch types of feedback using wearable haptic devices. So the first thing that we had to do, because this had not been done before, is to actually capture what are the social touches people use to communicate different types of emotional cues. So here, my student Sophia is wearing on her arm a capacitive sensing array sleeve. My student Mike is touching the arm and trying to convey some information. So we had a set of cues or prompts that we wanted people to display. For example, pay attention to me, people would do this. To convey that someone was happy, they would often grab and shake. And there are these different cues that people tended to use. So we collected data on this sensor array, which is shown here unwrapped, and each element is about 1 inch square, and then we'd capture the pressure distribution for a particular display. And then I don't have time to get into it now, but we had a mapping algorithm that would take cues that were displayed anywhere on the arm and mapped to a 2x4 array that's placed on the forearm. And as an example of one type of result from our experiments is we did show that people could recognize the cues pretty well, but we also showed that in a classic kind of human-robot interaction experiment that people also rated the valence, kind of the happiness versus sadness, and the strength, like arousal versus almost sleepiness, very appropriately given the cues that people are trying to display. So for example, love and calming are very similar. They have high valence, reasonable valence because they're positive, but they're not sort of exciting. Whereas these other signals maybe have higher arousal and typically good valence, whereas sadness has low valence and low arousal. So not only are people able to recognize these signals, they're able to kind of interpret them appropriately. So the last thing that I'd like to mention is that the types of information that we can display again through skin that's not the fingertips is going to be limited. And so one of my student Sophia's ideas was that, well, maybe you could have it all. So if you were to create a haptic device that could provide salient information and details through the fingertips when you wanted it, but still be wearable and not noticeable, and provide only kind of high level information when you wear it on the arm, how might you be able to do that? So she demonstrated that this was possible through a simple pair of vibration actuators, compared the ability to provide feedback on the fingertips and have people recognize details of vibration patterns, and also compare that to how people could recognize vibration patterns when it's on the arm. And you can see that fingertips only, the red line, is of course much better than forearm only, which is the blue line. But the nice thing is that if you feel sensations through the fingers and the forearm simultaneously, you do basically just as well as when you only display to the fingertips. So what this means is you could have a wearable haptic device, you're in a meeting, maybe you're listening to this talk, and you get a message from a friend, and that could be this very general information, like maybe the types of vibrations would tell you which friend it is, and you would feel that through your arm. And you wouldn't have to look at it. Nobody else would know that you're communicating. You would just feel it. But then you want to know, what is like the text message my friend is actually trying to send me? What are they trying to say? So you surreptitiously take your fingers and reach over and place them onto the wearable haptic device. And then you get a much more detailed information that you would only be able to perceive through the fingertips, because the skin in your arm doesn't have enough perception ability to do that. But all of this can be done in this kind of private information transfer, because it's all occurring haptically and not through sound or vision. So this is some of the vision of where we'd like to go with these wearable haptic devices. And with that, just like to thank again the students and postdocs whose work was featured, and my many collaborators and sponsors on this work. Thanks for listening.
Thank you so much, Allison. We already have some questions in the chat. I'm gonna unmute the person who asked the question, Quentin. I'm unmuting you. I don't know if it works. No, I don't think it's working.
Again, please.
So while we try to unmute Quentin, I can ask his first question. He say, hello, with respect to navigation, how precise would the skin be able to sense a difference in azimuth? Let's say that we indicate north. How much are we able to differentiate between 10, 20 azimuth? Is it possible, easy to train?
Yeah, that's a great question. So it depends on the mapping that you select, but it should definitely be possible, right? If you map like a particular angle to either a particular location on the skin or a particular amount of force on the skin, as long as you can scale it to the resolution that you need, you should definitely be able to provide feedback of that kind of information.
He has a second question. Are there specific skin conditions such as temperature, moisture, else that are optimal for haptics perception, or that you have to keep for the perception to work?
Yeah, that's a great question. You know, if you get very cold, it kind of knocks out your mechanoreceptors temporarily. And so if you get very cold, it doesn't work well. I think within normal temperature ranges, I don't know if there's been any real studies on it, but we've never seen an impact on perception. However, and work at EPFL has actually done this. People actually use temperature changes to communicate information. Like temperature itself can be a way to provide haptic feedback. It's not something that I've worked on, but definitely that's work that's been done at EPFL.
Thank you. We have Aoki that has also a question.
Yeah, great talk, Allison. Very stimulating, and a pity you're not here, but great to see you online. Yeah, very stimulating. I have a question compared to what you said at the beginning. If I understood properly, the thing where people feel compelled to move the hand in the direction you vibrate. That's very intriguing to me. So in fact, your system is tricking some reflex loop or feedback loop in the spinal cord or elsewhere. Do you know what type of feedback loop it is? Because we have a stretch reflex like to correct posture. It may be related to that, or we have these reflexes that if we hold on something and it's slipping, we quickly close. Do you know what are we tricking? What are you tricking?
Yeah, that's a great question. We also think that it's some kind of reflex. But we're not sure which loop it is. And let me just know, if anybody wants to try this at home, maybe you've even heard of it. It's a very similar sensation to what's known as the hanger reflex. So if you take a wire hanger, like the kind you hang clothes on, and you make it like you turn it flat. So normally it's hanging up like this, and you turn it flat and you put it on your head. You stretch it open, you put it on your head, and then you turn it a little bit so that it kind of pushes on your skin a bit. Then people feel this compelling, like they really want to turn their head. And you can see funny YouTube videos about this. And so with the hanger reflex, though, like on other parts of the body, you can get that effect a little bit, but if you vibrate it in addition to having the hanger reflex, it actually makes it much stronger. It even makes the effect stronger. It's, yeah, people have not yet identified exactly what loop is making that occur, and then why vibrations would actually enhance the effect, I would say, is also unknown.
But I think that people realize that the skin is a wonderful state estimator of posture, in addition to proprioception more in like muscle spindles and other things. So it's probably the skin informing us quite well where our limbs are and everything. So yeah, I will try this tonight. I have wooden hangers, but I'll improvise something.
Get a wire one. It has to be kind of stretchy.
It's very interesting, and maybe if I just may, to what extent is it spatially oriented? So could you can just feeling as if you're pulled and pushed? Is that correct? Or
yeah, that's right. So at the frequencies that this seems to be most effective, it manipulates the stimulation occurs probably in the Meissner corpuscles, which actually tend to be aligned forward and backward. So it works better forward and backward than like side to side. If like you mount the voice coil actuator this way, it doesn't work as well. But yeah, you can do it in multiple directions. And when we tried mounting things on different fingers in different directions, we also found that it doesn't do like a vector sum. It kind of works individually in different directions, but it only works as a vector sum if people are holding a vibrating object rather than separate vibration locations on the skin.
Yeah, super interesting. Yeah, thanks a lot.
Thanks.
Thank you. We have another question that I'm unmuting. It's Rana.
Yep. Thank you very much. Very interesting and mind-blowing talk, Professor. So I have just a few questions, or you can say that curiosity-driven points. So sensation of touch and pressure can be, vary from subject and object. So let's say if I'm wearing some haptic device, and my sensation of touch may be different from other person, and if some person, other one is touching me, he's you can say that pressure or touching can be different from person to person. So how we can standardize a device which can be, give us a constant or consistent feedback in these scenarios?
Yeah, that's a really good question. So what we've tried to do, for example, with this navigation experiment, is come up with an individual human model, and then we displayed a sort of person-specific algorithm for each person, and you can kind of get an average model, and it will still be effective for people, but it'll be more or less effective depending on the person. With your cell phone, you can actually, turn medium, high, low, or off. Some people turn the vibrations on their phone off because they just find it annoying, and like different people's annoyance levels, thresholds for vibration feedback also vary. So letting people sort of individually tune or scale can be appropriate, and that's even something they do on the teleoperated Da Vinci surgical system, for example, with like motion scaling. Surgeons can tune the level that they like. I think one interesting thing is that there are some problems that you'll never solve. There's a famous experiment from Dan Wolpert's neuroscience group called tit for tat, which is if you ever have two kids sitting in the backseat of your car and one kid hits the other kid and then they hit back and they say, oh, but she hit me harder, he hit me harder. And the answer is, like, perceptually, that's almost always true, because when you hit someone, the consequences, you have expectations of the consequences of your own actions, and your perception is sort of mixed in with what you expect based on what you did. But if someone hits you in the arm, you weren't expecting it, and so it feels like they hit you harder. And that's why, when kids fight, it escalates because the perception of the actor versus the recipient is just always going to be different. And so that tit for tat example is just sort of one reason why you'll never be able to make these sort of perceptions equal, because your perception is so wrapped up in how you act. And since we can't control how people act or what they think when they act, we can't necessarily control how they perceive the response, the haptic response they get from that action.
Great. Thank you very much for the answers.
Thanks.
We have a question from Serena. Serena, do you want to ask your question?
Thank you. Yeah, sure. So, I mean, I have the honor to meet you in person in Beersheba a couple of years ago, but every time your talk was super inspiring. So my question is whether, like, in your opinion and according to your results, it is better to train people on how to respond to a stimulus, or rather adapt the stimulus according to the personal response. And I was thinking about this like opposite possibility in fields like surgical robotics, where like a standardizability and a standardized response is like more like is required. So what's your idea on it?
Yeah, thanks for your question. I definitely think in fields like surgery, where there's already a lot of sort of training and standardization that has to go on, it can make sense that yeah, you have a process where each person has to learn the feedback. But when you think about consumer products, which is where we'll go if haptics is to be truly ubiquitous, I mean, people don't want to have to train, they don't want to have to learn unless it's done passively. So there are some companies looking at creating passive haptic bracelets, which, for example, take in sound and provide haptic feedback. And the thought is that if you do this for long periods of time, people will start to learn subconsciously the relationship between what they hear and what they feel. And then the idea is that eventually you wouldn't have to actually hear at all. You would just get feedback, haptic patterns on the wrist. So I would say that for consumer products, unless there's a way to train passively without the person having to do any work, it's never going to be successful. But in these sort of specialized scenarios, yeah, where training is expected, then I think it does make sense. And standardization would be important as well, so that people can communicate to trainees in addition. Thanks.
Thank you.
We have a question from Mina.
Okay, thank you so much for the great talk. And actually, it opens a lot of opportunities for providing feedbacks. I was wondering does the direction of the stimulation matters? For example, if you touch it like this, or I mean the sensor, if it touched like this, does it have a change to this one, or just the pattern of the sequence of the pattern that's different sensors stimulate matters?
Yeah, that's a really good question. So we haven't really tested, I think, every possible combination and direction. We do think, though, in most locations, like in the hairy skin, that direction doesn't matter. Like if we're going this way or this way, that you could perceive those equally well. But like I was responding to an earlier question, in the fingertips, it seems like some mechanoreceptors are kind of more aligned in certain directions. And then, you know, it becomes more important to, use those directions in order to, I guess, use what we know about those directions in order to provide like the best stimulation possible. But it seems to be more like less directional in terms of the hairy skin.
Thank you so much.
Thanks.
Allison, do you have time for one more question?
Yeah, sure.
Sorry.
You all do.
Quentin, I believe you have another question.
Yeah, hello. Thank you very much already for the first two answers. I was just kicked out of the meeting. So, but I was wondering if you are able, or if the human body is able, how many stimulation simultaneously is able to handle. So is it something like, for example, that we are, it's difficult to listen to two simultaneous conversation, with the sound? Is it the same with the haptic, or?
Yeah, no, that's a great question. So this is not something that we've tested, but I have read a study. I think it may be from Hong Tan's lab at Purdue University, of trying to do simultaneous feedback at different locations, and if it's different modalities of haptics can help, like a vibration versus a skin stretch versus a squeeze, then people can more separate and pay attention to the different forms of feedback. But vibration in particular, like the receptive fields for these mechanoreceptors are very large, and they also, you kind of tend to get saturation of the sensation. And so if you try to, say, display 3 different vibration signals all at the same time that are doing things, you can only do so much. When we did that example, the very last thing I talked about was like the 2 fingers on 2 different voice coil motors. Like we had to move them reasonably far apart, and 2 was the most that we thought we could actually use to communicate different sort of simultaneous pieces of information. So I would say with vibration, it's very, very limited in your ability to do that. But if you kind of maybe add in temperature and skin stretch and all these different sort of modes of haptic feedback, then I don't really know where the limit is, but you can definitely get more information throughput.
Okay, thank you.
Thanks for your question.
Thank you so much. We will stop here. Jan, if you want to take over. Thank you again, Allison. It was fantastic.
Great.
On behalf of everyone.
Yeah, thank you very much. So please allow me just say some words of closing. So thanks to you, of course, Professor Okamura, for having accepted to speak. Thanks to you, Alexandra, for the Q&A, and thanks to you all for attending the event and the great discussion we had. Just some brief highlights. So the next talks coming up is the CIS colloquium with Professor Susan Murphy from Harvard University. The title is Reused Reinforcement Learning, but Did It Work? You find it on the website. It's going to take place the 13th of December at 3:15 CET. And on the November 15th to 16th, we have a hybrid event coming up. This is the EPFL CIS Digital Twin Days, which will take place in person in Lausanne, Switzerland, if you're around, and online if you want to dial in from wherever you are based. Tickets for being in person on site are limited due to the pandemic situation, so please secure them as soon as you can. With that, please have a great evening, great day wherever you are, and hope to see you soon again. Stay safe. Bye.